ever wondered why some continents look exactly like puzzle pieces that snap together? According to a research, early map makers suspected that they were all connected. In the early 20th century, a scientist named Alfred Wegener called this supercontinent Pangaea. He thought different chunks of it broke off and slowly moved apart. Over millions of years, they formed the continent we know today. Wegener couldn't explain why Pangaea split up or how, but there was some confidence to support his idea. Fossils from similar plants and animals had been found oceans apart. The age and type of rock layers match up too. Wegener's theory of continental drift provided an explanation, but his ideas were taken seriously until long after he died.
Seafloor spreading. In the 1950s, scientists began mapping the Mid-Atlantic Ridge. It's a mountain range running 10,000 miles along the ocean floor. Tests revealed that farther you got from the ridge, the older the seafloor was. So a geologist named Harry Hess proposed a revolutionary idea. New seafloor was forming at the ridge and spreading outward to make room for more. In other words, the surface of the planet was moving. Hess called this process seafloor spreading. It seemed to indicate that rock was being forced up from inside the planet. Nowadays, we can see this rock formation in action. Wegener had guessed something like this, but he had no way to prove it at that time. The Earth's center, the core, is as scorching as the surface of the sun. All that energy wants to escape like steam inside a boiling kettle. It pushes outward, putting immense pressure on the middle section. From mantle standing in its way is the lithosphere, a rigid layer of solid rock. The lithosphere isn't like a smooth shell. It's cracked into pieces, each one into different shape, size, and thickness. We call those pieces plates. The Mid-Atlantic Ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet.
You can think of it like a pot of soup. The Earth's core is the burner, and the mantle is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents. A similar process is driving the mantle and taking the plates along for a ride. That movement is called plate tectonics. It's the engine driving the constant transformation of our planet's surface. Plates have been bouncing off each other for aeons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. The plates move about as fast as your fingernails grow, so we don't see the ground sliding under our feet, but we do sometimes feel it. It is estimated that the plates move around 1 to 10 centimeters per year.
Convergent boundaries is where two plates collide. Divergent boundaries, on the other hand, is where they pull apart. And transform boundaries is where they slide past each other. In all three boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. Plate movement drives volcanic activity too. At divergent boundaries like the Mid-Atlantic Ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth. Subduction zones. Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean converges with the lighter continental plate. The heavier plate gets pushed below down into the mantle. Some of it melts and the magma erupts farther inland.